I'm Justin Cormack, and I'm here because Xipeng unfortunately couldn't make it for unavoidable reasons, which is a real pity, but I've worked with him quite a lot on various things, and he's a good friend of mine. So in the spirit of open source, I said I would do his talk for him. So Xipeng is heavily involved in open source at Huawei. I know him through a bunch of security work we do together with the Cloud Native Computing Foundation. He's also involved in the Confidential Computing Consortium, and he's one of the nicest people to work with there is. So I work at Docker on security, and that's how I kind of met him. But this is very much Xipeng's talk. So, but all the faults in the delivery, of course, are totally mine. Xipeng gave a talk in Zurich, really talking about their use of RISC-V in accelerators for cloud computing, and that was really about AI accelerators in the cloud in sort of high power environments, and really just the kinds of things you need to do to integrate those with things like OpenStack, Kubernetes, those large scale things where really you need to know what kind of device you're talking to, lots of metadata about where things are, so you can route code to the right place where the hardware is, and so on. We're not going to talk about that today. It's already kind of moving onwards and outwards to edge and urban compute. So edge compute is something that's really become quite important in the last few years, and we're talking here about kind of relatively larger, higher-powered devices that sit like with edge gateways and around, in buildings and factories and in cars. And then urban computing is a term for the things that that sit closer to people. It's things that you carry around with you, that you wear, that are attached to your person. Entertainment, fitness, all those other categories of stuff that that you bring with yourself, rather than things that sit in a location, an edge location. And so these are really the things that the edge things are things that are attached to places and installations and buildings and factories and vehicles, whereas the urban stuff is the stuff that is attached to people, your mobile phone, your smart home, your fitness and travel and entertainment and all the things that we now expect to carry around with us, that are really close to us, or we use on a kind of constant, ongoing basis. And you're going to ask, well, what's this got to do with RISC-V, and why are these things important for RISC-V, and why is Huawei, who's obviously a big, RISC-V Foundation Gold member and very heavily involved in moving the platforms to RISC-V, why am I talking about this? Why are we talking about this here? So there's a kind of although there's this kind of continuum between near and near devices, far devices, bringing things closer or further away from you, it's actually really important that the software that runs on these things can actually potentially be moved between devices, and it can actually, we can overlap these things. So, for example, your in-car entertainment, ideally, you want the same interfaces and software as you have for your personal devices, and we want to invest in software that can move around and run between these things. Even though obviously the kind of scale of the devices is different, because the edge devices are large, have more power. Historically, running Intel or ARM devices, large sort of more server class devices, whereas and running KubeEdge, which is a Kubernetes thing we'll talk about in a second, and on Docker, containerized software that's kind of fairly moderately resource intensive, often built using LLVM toolchains, kind of traditional application development for sort of server-side things. And then the urban stuff really starts to shrink down. I mean, the mobile phone is the kind of only large, powerful device we really carry around, and even that's obviously much smaller than a server. But then many of the things like smartwatches and all the other little computers that you carry around are really microcontroller-based things. So LiteOS is Huawei's microcontroller OS. Again, we'll talk about that a little bit more later on. And you can still use LLVM toolchains for some of that, but we're also going to talk about some of the OpenArk toolchain, which is another thing that Huawei is developing for really designed for much more low-end devices. So if we want to interop and port these apps between these devices, then running everything across these things, across both edge and urban and all your devices on RISC-V starts to make sense. So you've got a really common infrastructure for all these pieces. So you can run software wherever it makes most sense. You can burst computation from your portable devices to edge devices. When you can move things around over time depending where it's most suitable to do the compute, because the whole kind of point of not doing everything in the cloud is so you can run stuff where it makes most sense at the moment you're at. So on the kind of edge side, one of the projects that Huawei is very much involved with is KubeEdge. So KubeEdge is a Kubernetes distribution for edge gateway scale devices. So it's not designed for really tiny things, but it's designed for medium-sized edge gateway type devices. But it is designed very differently from Kubernetes actually in the cloud, because it's designed for disconnected operation. So it's a kind of split control plane where there's a cloud control plane that controls the edge devices while connected, but then they also are able to run totally autonomously the rest of the time. So on the device, it can run Docker containers. It has a whole set of integrations with the kind of services you want on edge. So MQTT for talking to smaller devices from there, which is a messaging service, and a whole local control plane that can basically sit there, and it can deal with services that scaling up and down locally, deal with failures locally, and all those, and interface with the rest of the stack there. And then every now and when it reconnects, it can get new control plane, and it can talk to the control plane again, get an updated state, and continue. Whereas sort of standard Kubernetes just assumes that it's permanently connected because it's really a data center operating system. So this is a real attempt to sort of start disconnecting the cloud plane from the edge plane, and building something that makes sense from that point of view. RISC-V support here. I think if you may have gone to Carlos's talk yesterday about the kind of RISC-V in Kubernetes stack. It's getting there. It's really close. There's for the Kubernetes pieces, there's a whole bunch more pieces and more work that needs to be done for the whole KubeEdge stack, but that's kind of in process. There's some MQTT support. Then there's a whole bunch of ONNX, which is basically a framework for AI applications, which again needs support for things like RISC-V vector operations to support processing on vector machines, things like that. So there's work to do, but a lot of that stuff is really kind of starting to get there in terms of RISC-V support, and that's something that is being actively worked on. So on the control plane and the management side for the smaller microcontroller-sized devices, LiteOS is Huawei's IoT OS. It's all open source software that we're talking about today, and all available to anyone in the community to use. Historically, LiteOS has been targeted exclusively at ARM. but this is starting to change, and there's now early support for some of the RISC-V devices, the microchip PolarFire platform. There's early support for, and there's other things being worked on. Obviously, there's loads of board level support that you need for particular boards, but it's for any kind of OS for these types of things. But it's as these are small OSs, this is just a matter of dealing with interrupts and hardware devices on boards, and it's not a huge amount of bring up. So that works in process. It's work in process and happening, and very much RISC-V support is incredibly important for LiteOS looking forward as more and more of the platform gets moved to RISC-V. The OpenArkCompiler is a project that actually isn't so well known. This is a project in collaboration with the Chinese Academy of Sciences, and who are also big contributors to RISC-V as well. OpenArk is designed as a compiler for relatively lightweight code, but for example, things like mobile apps written in Java are designed to compile them down to small, lightweight, power-efficient runtimes. Again, historically, it's been largely ARM-based, but again, it's being moved to target RISC-V. And it has its own intermediate representation, Maple, which is actually, unlike LLVM-IR, is actually totally portable cross-platform, so it's kind of an interesting target. So this is, it's historically Java has been the main language target for OpenArk, but other kind of JIT and other platforms are potentially on the roadmap as well. And again, this is all open source software, so contributions are welcome. There's a lot of work to do with any of the, like with any kind of compiler target, bringing up a new architecture in terms of actually getting it, efficiently targeted in a way that's, will actually generate efficient code for particularly for small devices, for power, for power efficiency. It actually, so doing all those kind of stages of the compiler pipeline for RISC-V is in process. As I said, it was originally largely targeted around ARM, but RISC-V work is ongoing there. And we should see more support coming out very soon. There's actually a large amount of toolchain development going on, really, in Huawei and in the community around that. I think one of the things that strikes me as I'm based in Europe, is that in the software world, China has been a very historically very difficult place to communicate with because of the language barrier in terms of what's going on in software there. I've had to read mailing lists through Google Translate in the past for bits of software in China, but it's a big barrier. And I think one of the things about doing this talk was realizing how much there is going on in software in China, and we really need to find better ways of communicating what's going on in these different places. There's a lot of work going on the vector for LLVM on the vector extensions for RISC-V, because Huawei are very interested in supporting vector extensions for AI acceleration, and so there's a whole set of work involving bringing up vectors efficiently around assembly language support, intrinsic function support, and then actually auto-vectorization and supporting actually kind of vectorizing code efficiently. So that's all in progress. There's a repo there if you're interested in that. And I think that as vector hardware starts to actually for RISC-V starts to ship, hopefully quite soon, that'll be very important. There's obviously a bunch of benchmarking code, because actually if you're trying to build efficient compilers, actually doing benchmarking is really important. So there's a whole extended set of benchmarking around that. The Tiger compiler is kind of fun. It's actually a compiler for the Tiger compiler book, Andrew Apple's book. So it's a RISC-V compiler for education. So because obviously teaching people about stuff is just as important as actually doing stuff in production. And that's kind of a fun project for universities and students to use. There's a whole sort of work around analyzing code generation for LLVM for instruction scheduling and pipelining and so on, and register allocation, just to see, there's a lot of work in, from having a LLVM work to having LLVM work in efficient ways for things like supporting the, things like the limited subset of registers in the compressed extension, making sure that, compiling for different kinds of RISC-V architecture that may be more or less pipelined and so on. So all those things require, benchmarking and tooling and things like that. So there's a load of work going on in that. Code size, the future work that's really targeted, code size optimization. Again, there's been some talks about that over the last few days, but it's a very important area in terms of embedded systems and actually trying to make code small, efficient use of instruction cache, and generally allowing smaller microcontroller type applications to actually fit. As I mentioned, different types of microarchitecture need different optimizations. Code pipelining really needs, multiple issues. CPUs need very different things from microcontroller type CPUs, where the kinds of constraints that make things run efficiently are very different. So we need different optimizing backends for those types of things. Bunch of work on link time on the linker, always an issue, especially link time optimization and that stuff are becoming more important. The Maple IR that I mentioned, there's actually some work planned on converting that between LLVM and Maple, so that you could basically swap in different front ends and back ends for the compilers. And other kinds of issues. I mean, code obfuscation is actually an important area for some commercial applications. It's something that people care about. So on. So there's really a whole lot of work. There's actually a weekly newsletter about all this RISC-V toolchain work, which is goes out, but again, it's in Chinese. Again, it's one of these kind of language barrier issues that I think we need to do more work on trying to communicate across these language barriers and making sure that people are being able to collaborate together, because obviously a lot of these projects are things that people are interested in the rest of the world as well. So I think it's really important that we try and spend more time working with our colleagues in China. So thanks very much, and apologies from Zhipeng for not being able to give this talk, and I hope I gave it effectively for him, and so thank you very much.